The way I see it, like what we've been discussing, is basically we all have a common sense of what space is. So you, me, David, and I, we have the same notion of space, and it's filled in by some information, right? So the way you would like to think about it is that we're autonomous agents that act every day trying to plan what we want to do. For example, if we want to find an object, we need to plan what we do, but all of us have a notion of space, and we try to exploit the structure of the space when we plan our actions. So this is what I'm going to discuss. So basically, this notion of space, structure of space, is the notion of geometric world model, and I want to know how the geometry of world model influences behaviors. So this is, like, of course, I will define all these terms. And so this is the point of this article here, which tries to sum up the idea of how can you have autonomous agents, like that plan their behaviors, that plan actions, sorry, that have agencies on their actions. How can you make it compatible with a world model that is structured geometrically? And then an example of an application in a very particular foraging behavior can be found in this article here, where I'm going to, and I will discuss it today, which is how to get exact results for curiosity-based exploration when you change the geometry of the world model. Okay, so let's take a very simple example to start with. I mean, it's the example we consider in the foraging experiment. So you start with a setup where you have an agent, okay? An agent is a solid object with a solid frame. So what's in front, what's on the right, what's up, and it's looking for an object O, but it doesn't know where the object is. So for it to find the object, it needs to keep beliefs of where the object should be, right? And it cannot be a deterministic belief because its sensors are noisy. So when it's going to make an observation, so it moves, it doesn't know where the object is, it thinks it's here, it moves, it looks, it sees maybe a partial information about the object. This is because its sensors are noisy, and so it's going to update its belief of where the object is, okay? Now, in this setting, the way I had to define this experiment is I had to consider an object, an agent, and basically a global frame, system of coordinates to define the position of the agent and the objects. And most of the time, it's what you do when you do robotics, is try to keep a global frame on the experiment. And in fact, it's not what we do. Like as individuals, when I move, like my environment changes. I'm not considering the fact that I'm moving. It's what I see that changes. So you can have this kind of dual perspective on action and changes of frame, changes of points of view. Okay, so passive, active for physicists. Passive, active point of view on the displacement, movement. So basically, it's what we want to take into account in the model of agents that are able to plan their behaviors to resolve a certain task, is that they are able to have their own system of coordinates that change when they move. So they have frames on their environment, and when you change, your frame changes. So the simplest case is a Euclidean frame. You take a solid object, the agent is modeled as a solid object, it has its own frame, you write inside of the coordinates of this agent where the object is, and when it moves, then the coordinates of the objects that it's looking for changes. I mean, everybody has done this for classical physics, classical mechanics. Okay, so this is very important for us. So it's the key idea, how to take into account when modeling agency, the fact that the agent has its own perspective on the world. And so to do this, you need to relate the real world, so the world with a global frame, to the internal world model of the agent, so with a personal perspective, personal frame. So this is simply a map. You give yourself a map. So the agent is O inside of the environment. You give yourself a map that goes from the coordinates, the global coordinates, into the coordinates of the agent, so into a first-person point of view. Now, when you do the agent moves, for example, translates and rotates, its frame changes. So of course, you're going to have a transformation on the information it has on the object, because when it moves, so the frame, it's like the way it takes the coordinates of the object changes, and so you're going to have an effect of displacements on where it thinks the object should be. So in the Euclidean case, it's just a translation, right? I mean, like an affine transformation, translation, rotation. But you can consider things that are a bit more subtle. Like, for example, you could consider a projective transformation. You could assume that this frame here, change of frame, is a projective, say, projected chart. And then when you change, when you move, then this transformation here is completely non-obvious. Like you can have some magnifying effects, for example, which you don't have in the Euclidean case. So when you change frames in the Euclidean case, you don't have any magnifying effects because you just have an object. Like, for example, if you take a circle, you translate it, you rotate, the circle stays a circle that is translated. But it's not the case when you have a projective like transformation. You can have, when you go closer to an object, the object appears bigger. Okay, and then you need something more, like for what you need for any agent that has a sort of notion of agency, which is that it's a certain notion of planning of its own action, is you need a kind of notion of imagination. It means that the agent has to be able to say, oh, if I do this movement, if I go inside in this direction, will I be able to see the object that I'm looking for? So now let's sum it up into like this a bit more formal like definition. So an agent has beliefs on a state space of the world. The state space here corresponds to all the possibilities of where the objects could be, and the beliefs corresponds to where it thinks it is. It is of course probabilistic, stochastic, because the sensors are noisy. It can make observations, so it can update its beliefs, and then it can predict, so imagine the consequence of its own actions. The way you predict the consequence of your own actions is through a generative model. So okay, this I'm not discussing anything about changes of perspective, frames, projective geometry, or like the PCM. I'm just discussing about the very classical stochastic optimal control, MDP, so Markov decision process, partially observable Markov decision process, and this kind of a subfield which is active inference and free energy principle. Like for people who worked a bit with these subjects, it kind of feels that active inference is inside of reinforcement learning, or okay. Yeah, it would be nice to get questions on this. So yeah, formally, what is a Markov decision process? Simply you have a state space that encodes the world, like all the world model of the agent, so all the possible states of the environment, and then you can do an action, and this action will change the sets, the configuration of the elements in the state space. So for example, it will change the position of the objects I'm looking for. And then you have a reward function. You have a reward, and you want to optimize like a discounted sum of rewards, for example. But this is like when you have complete information on your environment. When you have only partial information on your environment, you need to add something more, which is the fact that you have observations that are partial. Okay, this is tautological, but you have a function that relates the state space to observation, which is that if I think the object is here, when I see it, I would expect it to be a bit around the place where I think it is. So this is something you need to add when you don't know exactly, we don't have complete information about your environment, but only partial information. You need to add the fact that you can relate, you have a priori a notion of relation due to your sensors to where I think the object is, and with respect to where I would expect it to be when I observe it. So the big difference we introduce, I mean, it's not a huge difference, it's a particular case of MDPs, is that we will consider action policies from the state space to the state space. So this corresponds to, let's say, the agent has an idea of the configuration of its environment at a certain time t. It can plan its action, and so it gets a new information on what the state of its environment would be at time t plus 1, and the y corresponds to possible observation with respect to the state of the environment at time t or t1. And we just say we don't want actions, or at least not just actions, but we allow to take changes of perspectives. So we associate to each action, like for example moving, a change of frame. So how do you write it formally? Formally, perspectives changing of frames, so doing this, internally correspond to a transformation on the space, internal space. So you can encode this through a group acting on the space, and we simply say that we want the state space to have a group acting on it. We want it to have the structure of what is called a G space or a homogeneous space, when you assume that you can, like every point is the same. So I'm not going to go into detail of this because it's not very deep. I mean, it's just a group acting on space. But this idea is really important. The fact that taking perspective on the environments, when you take when you change frame like this, and you change frame like this, internally you're just doing a transformation from one frame to another, and this can be encoded by a group. And so we introduce the notion of POMDP with state space structures by group, and we ask that the group, the way that the actions induce transitions from one state to another is through the action of the group, at least for some actions of the agent. And we're interested in particular into two cases, where first the state space is an Euclidean space and the set of transformations are affine transformations, first thing I was discussing, and second, when the state space is a projective space, and the second is a set of projective transformations. So I've been basically for the past, I don't know how much time, explaining what it is to have a world model, what it is to have a geometric structure world model, and basically what it is, what behaviors are. Where I didn't explain how you can have curiosity-based behaviors, how you can have exploratory behaviors. And I will spend like my time, rest of my time to discuss this. This is like very classical way. There's a notion of like foraging, how you can define an algorithm that computes a certain quantity that is responsible for foraging behavior. I will simply explain what it is and this, say how it can be directly transcribed when you allow to take perspective on your environment. So this quantity is epistemic value. Epistemic value is the quantity underlying curiosity-based exploration. So what does it mean? It means that, so remember that at time t, so the agent has certain beliefs about its environment, the state of its environment. After an action, it propagates its belief about the environment to what it thinks it will be, the environment will look like at times t plus 1. And then it's going to imagine all the possible observations it can do. So if it does, so I'm here, I think the object should be here. If I move, I would expect that the object is here. So if I see the object here, I can compare the amount of information I get from observing that the object is here with respect to what I thought where the object was. So if I move and I look at where the object is, I get more certainty of where the object is. So how do you compute this in practice? It's through epistemic value that I will just describe just after. But as you see, it's a quantity that depends on action. And for us, you can simply say that action is a change of perspective. Some actions, recall, corresponds to changes of perspective. So now you have a quantity that is no more defined on like finite sets of actions, but that can be defined directly on a certain group. So this is cool because now you can have a continuous function, you can have a function on a continuous space that has structure, and so you could imagine find some different optimization schemes like gradient descent, which you couldn't do before. I mean, not in the setting we consider at least. Okay, so more precisely, what is epistemic value? So it's computed by assuming that you have a prior on a certain space. So here X corresponds to the state space. You have a Markov kernel, so probability kernel between the state space and the observation, which corresponds simply to saying that for each of this observation, I have a stochastic observation. For each state, I have a stochastic observation that corresponds to this state. And then I can compute a joint distribution on the state space and the observations. And I just compute mutual information, nothing else. So I'm following the definition of epistemic value from this article here, active inference and epistemic value. So how can you interpret mutual information? You simply say that it's how informative, how far, how surprising is the a posteriori with respect to a certain observation to the prior. So the callback distance with respect to the a posteriori for a given observation with respect to the prior. But of course, observations are stochastic, so you need to mean on all possible observations. So the other algorithm we consider is simply the following one. So we start with a certain prior on the place where the object should be, and then we propagate this prior through the action of the change of perspective, which this you can do very naturally. So through this, like this formula here. So it's simply looking at what measure you get once you did your action. So you start with the probability distribution on a space or a certain prior, and then you act, and this changes the prior that you have. You compute curiosity for each of this change of frames. You take the one that is epistemic value, for each of the strings of frames. You take the one that is maximal. You say, okay, for this action, I am going to choose this action that I will realize. So it's going to give a consequence. It's going to propagate my prior to the next step. And then I get an observation which allows me to update my prior. And this is the simple algorithm we consider, but in two cases. The first one where the transformations are Euclidean, like affine transformations, and the second one when it's projective. And so the result is very surprising, is that in the first case, you don't get any drive for exploration. The agent stays still. But in the second one, it has a tendency to always get closer and closer and closer to the object. So you can see that the way that you change the geometry of the world model of the agent, it has an influence on its behavior. It's a very surprising result, right? So to get some intuition of what is happening, you can see that the agent with the projective world model basically is a bit paranoid. Or he's not very sure, not paranoid, but he's very stressed about its its own how the information he has is real, how much the information he has is reliable. A bit like me, okay, always stressed about am I really doing things correctly? Okay, so the agent, when it's moving in the projective case, it has a magnifying effect on the object, which allows it to get more information on the position of the object. So it's always going to try to get a magnifying effect on the object so that it's more and more certain on the position of the agent, of the object. Do you get this? Like, the idea is, as the way it perceives the object changes, it can delete a bit, make it a bit bigger, make the object a bit bigger, so it gets a better idea of where the object is. And so it's going to do this perpetually because it's never sure about where the object is. And in fact, like, this is a very nice Turing model, but how would you apply it? Now, it's not that naive what we just did, because we basically included the geometry of the state space and related it inside of the model of agency, and we relate it to behavior. And so now we have an explicit algorithm and framework to test how the geometry structure of the world model can influence the behaviors and, like, for example, the adaptive behaviors of the agent. And in particular, one thing we're interested in, how the group influences the stability of the representations. So this is ongoing work where we try to, like, do domain adaptation, which was I try to understand how geometrically structured world model allows to get better domain adaptation. Okay.
So I'm just going to very quickly, because, you know, this is the real scientist, this is a philosopher, I'm a specialist of nothing, I just have intuition and I know how to work with people. But this is some stuff we have done with another great mathematician, Daniel Benkin, without whom I couldn't have done any of that, of course. So it's just applications of what you basically heard about. In detail, it's not exactly the same math. I mean, for the geometrical aspect, it's the same principle, but in detail, in the way we optimize things, the choice of formulation of free energy or other kind of framework approximation of free energies, that if you look at the papers, it's a bit different from the framework that unified framework that Grégoire has been presenting with POMDP, but it doesn't matter. So here is just to say, if you read this paper, you will see that with this principle, we can explain here in particular the moon illusion, the famous illusion we all have experienced. You know, when the moon is down to the horizon, sometimes it looks much bigger than when it's up in the sky. It's an illusion. The visual angle is the same. It doesn't change anything. So with this type of model, with changing the parameter of the projective frame and how it affects the plane at infinity under free energy minimization, depending on the context of information, whether they are perspectival cues, distant cues, or no perspectival cues about the environment. When you minimize free energy, it acts on the geometry so that you get the moon illusion. And you can have different parametric versions, conformal or non-conformal, that get you the exact illusion. So then you can predict what the illusion will be, and you can reproduce using psychophysics in virtual reality a similar, the moon illusion, and people have to kind of rate how apparent size is based on comparison with a reference moon, and then you can switch environment on and off. And when you do that, you can get kind of psychophysical function that you compared with the nonlinear functions that are predicted by the model. And there is, it's preliminary in the sense there were not that many participants, but it sort of fit better than data from virtual reality, fit better the prediction than a linear model or other model. And interestingly, of course, since there are parameters, you can try to estimate those parameters that really characterize individually what are the projective parameters of the person. Some people might have projective parameters that make them, so to speak, more open in their attention in space. Some others may be more narrow. This is dynamical. All of that is under the control of that stuff. Can you move the next time? So then it is, as Ken was saying, this naturally generalized to kind of social cognition and behavior. Here, Grégoire has talked about epistemic drive. What we do is a bit, when we do robotics or this kind of things, it's a slightly more complex modeling. World models are much more complex than what he presented with this kind of toy model of an object in space. There are also affective drives. I'm not going to enter into that. Epistemic and affective drives kind of dynamically balance each other, one for foraging, exploration, the other ones for approach avoidance behavior related to reward punishment. All of that can be framed within the free energy framework or other type of optimal control, stochastic optimal control. And then we can implement robots that have models about each other. And in that case, can you play the little video? It's kind of a stupid example, but this robot believes that this guy doesn't like him. So it anticipates that if he approaches that cube, because it knows that he believes that this robot likes that cube, it will be basically closer to this robot. That's going to make this robot free energy goes up. And since he's influenced socially, you know, based on social psychology, you know, here is my tremors and my neurological stuff. So don't be surprised. I'm very awkward. It anticipates that, you know, that's not going to please this other robot. Since it computes itself its own free energy based on the free energy it estimates in the other robot, that's a way of implementing social influence. When it projects itself there, it knows that's not going to be good, so that's not good for him. And the poor thing, the only thing it can do is actually leave the room in order to minimize its free energy, because in its imagination, so to speak, he will take the point of view of this other robot. The other robot's point of view will see this agent being away, which if the other robot doesn't like it, it's better because it's smaller in its field of consciousness. And therefore, this nice robot leaves. Next slide. Oh, what time is it?
You're at 39 minutes altogether.
Yeah. So that's another example that just shows you we can actually generalize that to reproduce famous tasks on false belief that are and the processing of false belief and how you can take advantage of false belief in terms of, you know, or this guy believes that, you know, this object is the right one, that's the one he likes, but he's wrong, so I can go there, so he's not going to be here, etc., etc. I cannot enter into the detail. I prefer those guys to speak. So you can read the paper. Next slide to conclude. So now we are implementing an entire infrastructure, with servers for doing simulations connected to virtual reality in order to be able to now do the experimental science, to test all the hypotheses we can derive, because now we have math. So we can derive formal hypotheses, we can test them, potentially falsify the model, and we'll see where it leads us. Sorry for my... All right, good. Thank you much.